Hello, ladies and gentlemen, and welcome. So, I'm going to do this video to sort of help you with velocities as vectors. Um, we're going to take a look at velocity, which is a speed that has a direction associated with it. Now, we've been working with forces as vectors, and those were magnitudes with a direction. Now, so these are going to be velocities, which, as I said, is going to be a speed with a direction. The first thing I want you to know a little bit about is something called relative velocity. And it's the difference between two velocities. And it's given two objects, A and B, with velocities A and velocity B respectively. The velocity of B relative to A is given by V of B subtract V of A. Now, it says to read your textbook page 30, but we've got a new textbook, so that's not going to help us much or do anything for us. So we'll get rid of those. But let's sort of do a little example here. Let's say that I was driving in my car and I'm going 50 kilometers per hour, and someone comes up from behind me and passes me, and they're going 70 kilometers per hour. So I'm going 50. They come up and pass me, going 70 kilometers per hour. The relative velocity of me watching this person pass me, I will assume it will seem like to me that they are moving at 20 kilometers per hour, because I'm not going to think I'm moving. I'm in my car, I'm going 50 kilometers an hour, I'm already doing 50 of his 70, so when they pass me, it only seems like they're going 20 kilometers per hour. Now, if I was standing off to the side of the road, not in my car at all, that car would go by and it would look like 70 kilometers per hour. My car would go by and it'd look like 50 kilometers per hour. Okay? That's relative to me standing there and not moving at all. Now, let's say I'm driving down the road and I'm doing 50 kilometers per hour again, and someone's coming from the opposite direction, going 70 kilometers per hour. Well, at the moment that we pass each other, it's going to seem to me that that person is passing me with a velocity of 120 kilometers per hour. Because my velocity is going to be coming this way, their velocity is going to be coming that way, and right when we pass each other, they're going to go zipping by me, and I think they're going to be passing at 120 kilometers per hour. And just to bring this whole idea home, let's say I was going 50 kilometers per hour once again. And, oh, by the way, if someone's standing off to the side watching this, me going 50, them going 70, well, it's going to feel like I'm going 50 and they're going 70. It doesn't matter to this person. To me, it's going to seem like we passed that quickly at 120, not to someone standing off to the side. Now, let's say I'm going 50 and someone is going 50 kilometers per hour right beside me. I look over at them, they look over at me. It doesn't seem to us that either one of us is moving, even though we're both going at 50 kilometers per hour. So that is relative velocity. It's relative to what you're doing compared to what everyone else is doing. And you're going to have some questions in your homework working on that. Next, when we deal with velocity, we often deal with airplanes. So we're going to have to do some terminology here. When a plane flies, its velocity relative to the Earth is a result of the plane's velocity through still air. So that's how fast the plane can actually move on its own. No wind helping or hindering it. In still air, this engine can go this far, this fast. And we're going to add wind velocity to this plane. So the plane's going to go up in the air. It's got an engine. It can go so fast. And then we're going to throw wind at it. And the wind is either going to help or hinder what's going on with the plane. So we need to come up with some terminology here. We're going to let V represent the plane's velocity in still air. That's going to be called airspeed. We're going to let W represent the wind velocity at the time of flight. And R will be the resultant. So it's going to be those two things put together. And we're also going to call it ground speed. So that's what it's going to look like for someone from the ground watching the plane. So those two things are going to work on it. And here's a little example. So here's a plane. it's going to take off this way. It's flying like that. The wind is coming from this direction. Okay, so we pick the wind up, we put it down so we can add the two vectors. And what we get is the plane is going to be blown off course a little bit, so the plane's actually going in that direction. And we're going to do an example. So let's flip over and take a look. A plane is steering north 45 degrees east at an airspeed of 525 kilometers per hour. The wind is from north 60 degrees west at 98 kilometers per hour. Determine the ground speed and the track or the course or the direction of the plane. Okay. Now, on your workbook handouts, you've got a little diagram up here. I made a mistake. I wrote on my originals. Ignore it. We're actually going to write something that looks identical to it, but ignore it so that we can redo our own. Either erase it or cover it up with whiteout or do something. I guess erasing won't work. In your textbook, they show you how to do this, and I've asked you to read it, but they do it differently than I do. I set up a cardinal directions, okay? North, south, east, west. They don't in your textbook. I think there's value in this. I don't really care which way you do it, but we'll go from there. We have a plane that's going to be steering at north 45 degrees east. So it's steering like that. And it's going to be 45 degrees here and 45 degrees here, because that's what it means to be north 45 degrees east. Now our airspeed for this puppy is going to be 525. Now I happen to make that 525, so if I have any other speeds coming into this, they either better be larger or smaller than it relative to the numbers that I have. So the wind is from, now that's really important, guys, come on. We've got to really read here. It's from north 60 degrees west. So I've got a wind that's coming from north 60 degrees west. Now I made it shorter because the magnitude of that wind is only 98 compared to 525. So that's going to represent 98 to me. That's going to represent 525. This is my wind coming from north 60 degrees west. Now that wind I could draw with an arrow coming like this, or that wind I could draw with an arrow coming through like that. And we talked about that when we talked about forces maybe kicking a ball. If I have a force kicking a ball, perhaps I could have the ball shown with the force kicking it, or I could have the ball shown with the force traveling through it and the ball moving. It doesn't matter. It's the same thing. So here's my wind coming from north 60 degrees west, and here's my wind continuing through the origin. Now, if this is 60, this will be 60. Okay, so what I'm supposed to do is determine the ground speed. Now, the ground speed is going to be what happens when the plane's velocity interacts with the wind. So you've got a wind here of 98 kilometers per hour. So it's supposed to be affecting the plane. Now I have a choice. I need to add these two vectors. Okay, I need to add these two vectors. I would be very wrong to connect it like this. I can't go from here to here and then magically return and go from here to here and say somehow that's moving in that direction. This wind is going to be acting on the plane. I'm going to pick it up and move it, and I'm going to put it here. Why? Because I can. Pretty much that's the real reason that's going on here. It's a free vector. I'm going to take this vector, I'm going to add that vector, and guess what? It's going to give me a resultant. That wind is going to push the plane off course just a little bit, so it's now going like that. And that's going to be my ground speed, or my resultant. Okay? So once again, I took my wind, it's coming from here, I could show it going through there, and I picked it up and moved it there. I can move things around anyway. I could move the plane speed down to add it to the wind, but notice that would move it off of the origin, and getting direction would make things more difficult. Okay, so where do we go from here? Well, we need some angles in this triangle. I've made a really nice triangle. I need some angles. This is 45, and this is 60. Which means that this whole thing is 110. That means that this whole thing is 110. Oh, 105, I can't add. Not sure where 110 came from. So 60 plus 45 is 105 degrees. So, and what I have here is zip, zip, zip. I have TPT alternate. And for most of us, you guys know that as the Z pattern. So that's 105 inside. So what do I want? I've got two sides that I know their length. I've got one angle, and I want the opposite side. Well, that sounds like cosine law to me. So r squared, or the magnitude of r squared, that was ugly. The magnitude of r squared is going to equal, I don't feel like reading these numbers out. You can read them. Now you got to know this formula. If you don't know it, then we're in trouble. Okay, so that's the cosine law. There it is. It's all on the screen now. So I'm going to take my calculator, and I'm just going to do it as soon as I find my calculator. So you all have different calculators. You have to figure out how to use them. So 98 times 525 times 2 negative plus 98 squared plus 525 squared, second function square root. So the magnitude is going to be 558 kilometers per hour approximately. Okay, so what's happening is this wind is acting on our plane, and it's actually pushing it along a little bit. Not only is it pushing in the direction that it's going, and it's making it going a little bit faster, but it also pushed it off track a little bit. Now that's the question. How far off track? Well, I need to measure this angle. The angle I need to measure is this one, okay? Because then I'm going to say that my plane is going north, whatever that is, east. Now, to be able to get this whole big thing, that part's going to be 45, but this part is not 45. It's only part of 45. This angle can be found, though, in this triangle. This angle, theta, is actually this angle in between here. Okay? So for the direction, what I'm going to do is I'm going to say sine of theta, which is this guy here, over top of 98 is going to equal sine of 105 over top of 558. So, doing this, it's going to be sine theta equals 98 sine 105 over 558. 105 sine times 98 equals, divided by 558 equals, second function sine, and it's about 9.8 degrees. That angle there, 9.8, which means that this whole angle will be 45 plus 9.8. So, therefore, the plane has a ground speed of approximately 558 kilometers per hour and has a direction or course of north 45 plus 9.8 east. And I put that in just so you know where it comes from. Oh, you can't see what I'm writing. I'm so sorry. I put that in just so that you know where it comes from. And so it's going to be 45 plus 9.8 equals north 54.8 degrees east, which is that big angle right there. And that's how you work with velocities. Now, something to consider. When you're doing your homework, I want you to be aware of something. Notice this one, we had this vector, we added this vector, and we got a resultant. Be on the lookout for me giving you a resultant and you having to determine one of the components. Okay, now listen to that again. In this one, we had two components, we put them together and added to get the resultant. In your homework, you're going to come across ones that have a resultant and you have to determine one of the two components. Be on sharp lookout for that. I think you can handle it. And that's it for that example.